The next two examples that we're going to look at are going to look at applications of exponential functions. And the first thing that we're going to look at as an application is compound interest. Have you heard of compound interest before? When you put money into a bank account, you get interest, okay? And when you get interest, the way that it works is they pay you maybe every month. So let's say you start off and you put in, wow, a shiny $1,000. It's not very shiny yet, but hopefully it appears on the screen eventually. Should we try it again? Huh. There it is. Nice and slow. So you have a shiny $1,000, and let's say you find out a bank that pays a really high interest rate, but we're just using this because it's easy to do the mental math. 10% per year. What is 10% of 1,000? Okay. Let's say I'm 100. I'm going to actually we're going to have, just to even easier do the mental math, we're going to start with $1,200. It does make it easier. It will, but 10% of 1,200 is 120. Now, what usually happens is that the bank pays you interest once a month. So if they're going to pay you 10% interest in a year, which is $120 in a year, they're not going to pay you $120 every month. How much are they going to pay you in the first month? $10, because 1/12 of 120 will be $10. So at the end of month one, which I'll just go month one, you will now have $1,210. And the way that compound interest works is then the next month they say, well, how much money did you have in there? You say, well, I had $1,210. What's 10% of that? $121. And now what portion should they pay you? 1/12 of that. So you're going to get an extra 1/12, which is going to be not very much, but a little bit. So then you'll add another $10 month two. And if we take 121 and divide it by 12 perfectly, you get an extra 88 cents. Sorry, not 83 cents. So now you have 120 and an extra 83 cents. Yeah, it would be nice. Then you'd get $10 every month if you had $1,200. And so this keeps on going, and at the end of 1 year, right? At the end of 1 year, you're going to have more than the extra $120 that you expected. In fact, if we kept on doing this, yes, you have to have money.
I guess I don't have interest.
So here they're doing $100 at 2%. But this is the idea of compound interest. And if we connect it to our sequences unit, so we started off with $1,200 month one, and we multiplied that, right? To get 10% more would be multiplied by 1.1, right? Does that make sense? Here, let's look at the math first of what they're doing here. Okay, they're giving 2% on 100. So you get $100 plus 2% of 100. After year one, you would have 100, if you factored it out, 100 times 1.02. That would be after 1 year. If you did it a second year, you would have that 1.02 happen twice. And a third year, you would have that 1.02 happening 3 times.
Why do they do like 3 squared instead of just times 2 times 3?
Because when your amount, right, to go from here to here, we multiplied by something. If we want to figure out what we multiplied by, we could take 1210 and divide it by 1200, because that's how geometric sequence works. And we've multiplied by 1.00833. If you take this number and divide by this number, you'll find out you've multiplied by the same number again. How do we come up with this number, 1.0083? Well, it's going to be 1 plus 10% divided by 12 months. Because we got 10%, but it had to be split up because we're only collecting 1 month of it because it was compounded monthly. So taking this idea and putting it into a formula, and this formula used to be on your formula sheet, but now whenever they ask a compound interest formula, they just give you the formula. The formula looks like this. And we're going to quickly, on the side here, describe what each of these things mean. So in our compound interest formula, we have the value A A is the amount after t years. P stands for your principal, and that is the amount you start with. R is your interest rate as a decimal, not as a percentage. So if it's 5%, you would change it to 0.05. T is the time in years, and N is the number of compounding periods per year. And almost all banks work on compound interest. The problem right now is if you guys have a bank account, you're probably getting very, very, very little interest just because interest rates currently are so low. Does anyone know what interest rate they make from their bank? 3%? That's very high.
I get like a penny
A penny a
a month.
month.
I don't get any.
Okay, 3% is really good for right now.
I only get 3% because when I signed up for my bank account, it had the same promotion, so I only get it for this year and then next this year.
Okay, so you get it for this year, and then after that, it's done.
Yeah.
And then it goes down to, I think my interest rate might be 0.005% or something really little. I can't remember the last time my bank account gave me any interest in one bank account that I have. I have another bank account that I think pays 1.7% interest, which is still pretty small. When I was your age, my student account, I think, paid 7 or 8% interest rate. The number of compounding periods per year. So if it's compounded monthly, in other words, the example that we gave where it was paying us once a month, then you would have 12 compounding periods per year. And a lot of banks work on a monthly basis. Okay? Some interest rates are compounded on a daily basis. Well, it's part of it is figuring out how much you had at the beginning, how much you had at the end, how much interest they owe you on that section, and going from there. What's that? And sometimes checking accounts don't provide any interest whatsoever. Now, for the most part, the amount of money you have right now, for the most part, isn't enough to make the interest crazy. Okay? We're going to find out some interesting questions with interest later. But for right now, we've got our compound interest formula. In the textbook, they use A0 instead of P. So sometimes you'll get different notations. They use I instead of R, I for interest rate. And we call, because it is an exponential function, that part of your fraction, that part of your formula, the growth factor, how much it's growing by. So let's look at our first example. And again, if you were given this question, you would be given the formula as well. A principal of 1,500, so we'll write out the formula. A principal of $1,500 is invested at 4% annual interest compounded quarterly. Quarterly means 4 times a year. To the nearest quarter of a year, when will the amount be 2,500? So we start filling in information here. We want the amount to be 2,500. We want the principal, well, the principal starting at 1,500. The interest rate is 0.04. It's compounded 4 times per year, and we want to solve for t. So up till now, we have been solving these by trying to get the bases the same. And most of our equations that we've been using have been things on our powers chart. Is 2,500 on our powers chart? No. Is 1.01 anywhere on your powers chart? No. So the numbers, when we get to a real life problem, tend to not work out nicely like the just sort of mental math problems that we do to start with. And right now we haven't learned logarithms yet, so we can't solve this algebraically. The only thing we can do right now is solve it with a graphing calculator. So what we're going to do with our graphing calculator is we're going to type in one side of your equation into y1 and the other side of your equation into y2. So I'm going to clear out everything else that we have. The one side of our equation was 2,500. The other side of our equation was 1,500 bracket 1 plus 0.04 divided by 4 to the exponent of 4x. Now, if you hit graph right now, can you tell me why you'll probably not be able to see y1? What is y1? What kind of graph is that? It's a straight line at 2,500. So if you have your graph set from -10 to 10 like mine, you will not see that line at 2,500. What kind of graph is the right-hand side? We'll let it pretend to graph for a while. What kind of graph is this? It's an exponential graph. What's the parent function? 1.1 to the x. So the parent function would be an increasing exponential. What's happened to it? It's been stretched by 1,500 and had a horizontal compression by a factor of 1/4. So again, even when we're using our graphing calculator, we have to quickly be able to analyze the graphs that we have to get a general sense of what the equations are. So we have one graph that's an exponential function, the other one that's a straight line, and we want to find that intersection. What we have to do is get our window to be able to see that. So going back to my graphing calculator, going back to my window, well, one thing I know for sure is that my straight line is at 2,500, so maybe I'll make my y max at 3,000. And now I'm going to graph it again just to see if I can see that straight line, and I can. The question is, can I see the graph swooping up? Yes. Is it going to swoop up and cross on my screen? Oh, so close. So now I have to go back to my window and say, I need to see a little bit more to the right, so my x max at 1020 will probably be enough. Once you've got a window where they do cross, you're now going to be able to solve this, because you can solve it by going second, calculate above the trace button, number 5 where they intersect, enter on the first curve, enter on the second curve, enter when it says guess, 12.83. All right, questions for practice, but we're not going to work on these right now, are 12 and 13.